Okay, maybe we'll get things started because I see that now people are starting to filter in. So I'd like to welcome everyone to the second IMR seminar for this year. Before I introduce our distinguished speaker, I'd like to just do a quick land acknowledgement. McMaster sits on the traditional territories of the Mississauga and Haudenosaunee nations and within the lands protected by the Dish with One Spoon Wampum Agreement. The agreement is also a covenant with nature: take what you need, leave something in the dish for others, and keep the dish clean. Okay, with that, it gives me great pleasure to introduce our speaker for this afternoon, Professor Jason Hattrick-Simpers. Professor Hattrick-Simpers is currently in the Department of Material Science and Engineering at the University of Toronto. He received his bachelor's degree in mathematics and physics from Rowan University in, I believe, New Jersey. He then completed his PhD in material science and engineering at the University of Maryland. After receiving his PhD, he started his career at the National Institute for Standards and Technology in Gaithersburg, Maryland, where he spent a number of years and spent his time there investigating corrosion resistance in alloys. He did some work on additive manufacturing of thin films. And he developed his interests in the use of artificial intelligence in materials research. Very recently, he joined the University of Toronto, so back in July of this year, 2021, and there he is carrying out the unenviable task of setting up a brand new research group in the middle of a pandemic. So I'm sure that comes with lots of challenges. In addition to his position at the University of Toronto in the Department of Material Science and Engineering, he is also appointed as a research scientist at CanMet here in Hamilton. So he spends a significant proportion of his time just down the road from McMaster University. And so today, as I said, he'll deliver the second BIMR seminar for the year and also the second talk in a short series on artificial intelligence and machine learning and applications of these ideas and tools in materials research. His seminar is entitled How Robots Can Teach Us to Trust AI. And with that, I'll turn the floor over to Professor Hattrick-Simpers.
All right. Well, first of all, thank you all for attending. Thank you all for the invitation. As Alex said, I work right down the road in Hamilton, and I think that NRCan has traditionally had a very strong relationship with McMaster certainly since we moved right across the street from y'all. And so I really hope that my seminar helps to continue to promote those types of interactions, both with NRCan, but also in my other hat here at University of Toronto. And so title of my seminar is How Robots Can Teach Us to Trust AI. And as I was discussing with Alex just now, I want this to be a conversation. I am going to start everything off by saying I'm an advocate of the use of AI and automation in material science, but I'm also a skeptic. And I think that we should all have this sort of raw enthusiasm for the topic because it will allow us to do really interesting work moving forward as scientists, but that we shouldn't let go of this hesitance, and we should never let go of the actual creation of science, right? That should always be a human endeavor. Okay, so let's get started. And to my point, you know, these two young people sitting down playing chess with laptops in front of them are basically doing what I am going to advocate to you all we should do with AI. AI is a tool that allows us and helps us to make better decisions faster, But when it really comes down to it, it's always the human that should be moving the piece. It's always the human that should be deciding what's the next experiment or what's the next system to look at, using the deeper level of heuristics and creativity that we have that we can't encode into our AIs. Okay, so we start off this seminar. People throw around the term AI, they use machine learning, and they use them interchangeably often. What's the difference? Our friends at Google Accelerated Science will tell you machine learning is the part of AI that works. I tend to think of it a little bit differently. I think of AI as the output, right? It's a trained, thoughtful, and productive graduate from a prestigious material science department, such as at McMaster. Machine learning, those are the educational units and the assessments that we use to evaluate how well a machine is learning to do a specific task, or how well a student has learned kinetics or thermodynamics. So sort of keep that in mind. I'm going to drive hard and we're going to talk about AI, but always in the back of your mind, an AI should be able to make decisions by itself that show some level of intelligence, and often underneath it is a bunch of machine learning techniques working together. Okay, so my lab at the University of Toronto, we call ourselves the Autonomous Discovery of Alloys Group, or AutoDial. And our emphasis are sort of in the areas that I'm most interested in. First of all, my background is in high throughput experimental materials discovery. My whole life has been devoted to creating parallel or rapid serial synthesis and characterization tools and applying them to look for new materials with interesting properties, or to understand materials. We build autonomous research agents, robots, right? Up north, you all call them materials acceleration platforms, but the goal is to create something that's able to select the next experiment, conduct it, get some information out, decide on the next experiment, maybe talk to me, and iterate. We have an emphasis on how do we establish and promote trust in AI in the community so that we don't plummet too deep down into this trough of despair that's coming after the peak of expected or inflated expectations. And something I'm very passionate about is providing open science platforms, data, and code to enable people from all around the world in all different socioeconomic backgrounds to be able to participate in science and maybe show us something that we haven't seen before and change a conversation about a particular materials topic or a brand new phenomenon that people hadn't considered. Okay, so we're material scientists, or at least a portion of us are, or materials chemists. We understand that there are a lot of really cool technologies that are just sort of waiting around for a new material solution. Solar fuels, if you could find platinum group-free catalysts for more or less any application, then you're a rich person. Gas and steam turbines, additive manufacturing in particular, there's this problem where when you three-dimensionally print something that's got the composition of an Inconel 718, it doesn't have the properties or the microstructure of Inconel 718. And then for my own personal interest, I really like working with corrosion-resistant materials. It represents a substantial part of the mitigation and remediation of corrosion represents a substantial part of the gross domestic product in the US and Canada. The numbers right about the same. But there's also a large sociological or societal impact that we'll discuss later on. But these materials are here, they're waiting for us, right? So as a material scientist, I think about the elements as being ingredients for a risotto, right? So there's maybe 30 non-toxic-ish, depending on the application. I noticed that lead's there. Depending on the application, it might be okay. Which means that if we only consider 3-component systems, we're looking at around 4 million compositions that need to be identified if we're looking for any particular new material, right? Keeping in mind modern state-of-the-art alloys, they contain 5 and more intentionally their elements and a slew of elements that we would prefer not to be there. Sulfur and high temperature turbine blades is a great example of the latter. But even having the correct ingredients doesn't make the risotto, right? We also have to process these materials. And processing spans many different orders of magnitude if we just consider cooling rate. On the right, you've got melt spinning, which has a nominal cooling rate of 10 to the 7 centigrade per second. And on the left, you've got an example of a meteorite that's got a cooling rate nominally on the order of 10 to minus 12 centigrade per second. So it's roughly 20 orders of magnitude difference in their cooling rate. We use melt spinning to discover, we were using them for metallic glasses, but quasi-crystals. But more recently in Russia, people have discovered quasi-crystals embedded in meteorites. And so there's this huge range of potential processing, just considering cooling temp, not temperature, time, any of these crazy profiles that we have to explore. And so we want to be able to explore these processing in parameter spaces more efficiently. And there's a lot of enthusiasm for using AI. This is a slide borrowed from Bryce Meredith at Citrine. And it really drives home the fact that materials are not the usual AI use case. I'm reading a book right now called Statistical Rethinking, and the statistician in that also nails home that the AI techniques that we're using from sklearn or TensorFlow and so forth were not designed with our specific applications in mind. And so they have blind spots. You know, if we think about Google, we think about big data, 10 to the 8 examples. Materials, we're talking, you know, if you can get 100 examples, you're doing pretty well. The prediction task, you know, doesn't matter to Netflix if they recommend a couple of movies that I'm not interested in, as long as they can, you know, 5 times out of 10, 7 times out of 10 recommend something I like. So they just want a pattern match. As material scientists, we like patterns. Patterns are nice. They tell us a little bit about mechanism and give us a more fundamental understanding of the universe around us. But we really want the outliers typically, because those are the materials with interesting properties. And it just keeps going down. You know, we want domain knowledge. We want physics-aware science. We want uncertainty in our data, in our models, and we want it propagated all the way through the chain. And when it's all said and done, we want to have a model that we can understand. They use the term interpretability here. That's fine, but those are typically very simple models like linear regression or lasso or decision trees. We could even accept explainable models where we don't necessarily get a model out that we can directly look at, but as long as we have an additional model on top of that that can tell us things like feature importances, well, then we can begin to rationalize what the model is picking up on and try to understand why it makes the predictions it does. I want to emphasize this isn't an obstacle, that AI wasn't built for us. It's an opportunity. It's an opportunity for us to work with our computer scientists and statisticians and sometimes sociology colleagues and build something from the ground up that's universally useful and maybe attacks problems that they're also interested in. All right, so let's talk about sort of generally where we use AI today. And what you can say if you look through the literature is that we basically use it across the entire material science, design characterization, and knowledge extraction pipeline. We use it for experimental selection, new data acquisition, for instance, optimizing synthesis or optimizing how long have I been counting on my detector? Have I counted long enough for measurement optimization? We use it in data processing, pre-processing, and feature identification. So clean the data, take 1,000 spectra, project them into latent variable space, and then try to build models from that, or from those sets of features, try to identify what are the important ones for predicting property. And then we use them in knowledge extraction, data minimization, and generating actionable information. And the question that we were asking ourselves a couple of years ago is, if we're doing this, why don't we just close the loop? We're already applying these in so many different parts of our pipeline. Could we just close the loop? And we'll talk about closing the loop later on. Recently, a bunch of us from NIST sat down and we sort of wrote up a perspective piece about the use of scientific AI in material science. And we identified opportunities, right, in this vertical or the horizontals, right? So the creation and generation of scientific AI, the buildup of cyber physical infrastructure, developing and enhancing trust in AI, and then workforce development, right? And so you go from things that are very social in nature, workforce development, to very technical, like the development of brand new scientific AI. And then we identified a series of paths forward. The collaboration between material scientists, computer scientists, mechatronics people, statisticians, and so forth. The build-up and development of autonomous research platforms, dissemination, generation of reference data, establishing consortia, and disseminating best practices, which, again, sort of fall in this spectrum from things that don't exist right now, we have to make, we have to develop them, to things that we can begin to deploy, i.e. best practices. And in total, we came up with about 28 of these intersecting opportunities and paths forward. And in my talk, I'm really going to focus on autonomous research platforms, how we can use them to develop scientific AI, what does the cyber physical infrastructure look like, and I'm really going to nail down on reference data and how we can use that to develop trust in AI and to generate models that are predicted on scientific uncertainty and promulgate those. So a couple of years ago, I sat down with a bunch of my colleagues at SLAC, at Stanford, at Northwestern, and we sort of had a question. How quickly can one really discover amorphous alloys? They're complicated to look at using density functional theory. If you really want to project into high dimensional compositional space, molecular dynamics isn't really going to get you there because of the need for interatomic potentials. But we have a lot of observational data. We have Landau-Bornstein, and we can pull that out, and we can create training sets from that. And then we have some ideas about why things form metallic glasses, what are the properties of elements, and we can use those to generate attributes to describe each material, each instance of whether it formed a glass or not. Here are its features. We can use those attributes in the training set to build up machine learning models, which we can then use to project into that 3 million different composition space and predict whether or not something is going to form a metallic glass or not. We can then go back after the fact, select some systems based off of criteria, perform a high throughput experimental search, and voila, you have discoveries. You have true positives, it was supposed to form a glass and it did, awesome. You have true negatives, it wasn't supposed to form a glass, it didn't, hooray. And you have these off-diagonal options where it was predicted to form a glass, but it didn't, or it was predicted not to form a glass, or it didn't. Sometimes in traditional material science, we think of these as defeats, right? These are places where the model was wrong and there's a little bit of room for despair. But for a machine learning model, that's fantastic. Not only did I learn about that new system where I was wrong, but I can now propagate my new understanding across of all the composition space. And now my model is better holistically across all of the different parameters. Awesome. And you can find new metallic glasses that way. You can also take that data out, look at the models, look at the observations, have a scientist sit down with them and generate new knowledge. And so it was awesome. It was cool. What we found was that we could accelerate the rate at which we discovered new metallic glasses about 200 times. And just to sort of give you an idea, the original Landau-Bornstein data set was about 7,000 entries. Our current data set exceeds 30,000, and there's probably about 5,000 or 6,000 that are sitting on my desk that need analysis still. And it was fantastic. The new discoveries were all around waiting for us. So you can find things like new materials with promising properties, where, for instance, we discovered a new set of metallic glasses that exhibited hardnesses and wear resistances that were on the scale and comparable to diamond-like carbon, right? And in this particular instance, it was an example of there being a lot of meat left on the bone. For about 50 years, people had been sort of looking around in this particular area, in that ternary. And what we found was that the best glass formers with the best properties were up here, far away from where anybody had thought to explore previously. And it's not just new discoveries, not just new materials with fantastic properties. The science just comes out of it because you're churning through this parameter space so quickly, so holistically. The data come out and you can compare model to physical intuition and generate new ideas. So this is an example where one of our collaborators, Kevin Laws, we asked him, why does this particular system always show in this region on this binary and down into the ternary? Why is it always glassy? And so he took the liquidus projections, he superimposed them upon the places where we had seen metallic glasses, and, just complete bit of human intuition realized that it was the lavas phase, the zirconium cobalt 2, that was the most likely culprit for why we were able to form glasses so easily in this alloy. And so what he hypothesized was that the ordered lavas, that's an AB2 structure, was inhibiting the growth, was kinetically inhibited under the conditions of our deposition. And therefore it was so frustrated, it couldn't form long range order. It formed only short range order and then became glassy otherwise. And so there's opportunities. There's green fields around us. The problem that I quickly discovered in that particular project and in subsequent projects was that we can't science fast enough, right? In a comparable project looking at thermoelectrics, we were doing synthesis and processing at University of Maryland at NIST. Josh Martin was doing thermoelectric characterization for us at NIST. And then we were doing our structural characterization at SLAC. And what I discovered very quickly was that I was burned out. The model validation latency was about 4 ternary systems a month. So we could look at about 48 ternaries per year, which is an amazing rate, not gonna lie. But the model training and prediction latency was less than a day for all reasonable systems. And so the folks at Citrine and Northwestern and Logan Ward at Argonne would generate a set of predictions and then have to wait 3 months until we had beam time to get information back. And then the next day, churn out the next set of predictions and wait some more. So what we need, if we're really going to incorporate these types of techniques more actively into our experimental or even computational pipeline, is scalable synthesis and characterization that can match AI lead generation. And so this idea, these materials acceleration platforms, Benji Maruyama from Air Force Research Lab demonstrated the first one, arrays on carbon nanotubes. It's a field, right? It's a field and it's a rapidly growing field. And the idea is that you have an idea, you initialize the experiment, and this is done as a human AI tandem. You define objectives, you specify constraints, you provide the AI prior knowledge. You then say, okay, with this plan, predict, make predictions, balance this trade-off between exploration and exploitation of your model predictions, decide what you're going to do next, make it, characterize it or simulate it, analyze what comes out of that pipeline, extract and represent the knowledge, interpret and increasingly explain or reason and understand what's happening, and then sort of continue that iteration until you've achieved your objective, at which point you conclude. We've achieved the objectives, we have some scatter, but we're hitting consistent results, maximized property, no longer are we really touching the uncertainty. Report out that knowledge and update the repository and allow a human again to sit down with the data and either decide to come back to this initialize step or to move forward with scale up and patenting of the idea. What's awesome is that it's a space, it's brand new, and there's so many challenges. Data and metadata capture standards are wild right now. There's no there's no consensus. There's this opportunity for uncertainty quantification and things like synthesis, where traditionally I would just write something down in a notebook and then replicate it in a paper. Now we have a method of not only tracking it, but building statistical models from it natively. There's uncertainty quantification in the characterization and the ability to propagate both of those uncertainties through all of your predictions. There's also uncertainty in your model, which needs to be propagated. There's the need to quantify our bias and machine learning bias. And there's an opportunity, huge opportunity, massive opportunity for the integration of physics into artificial intelligence. And when you really think about it, the sky's the limit. Because at the moment where you've been able to successfully decouple your AI from your automation, you have this place where suddenly you build up automated lab infrastructure that's capable of doing the full synthesis and characterization suite. You build up the ability to run simulations and even to run AIs. But decoupled from those, there's a place for central data storage and a resource manager. And so somebody like me can sit in my basement writing AI, interacting with the data that's been taken on these two systems, generate a model, generate a prediction, push that to the resource manager, which then decides which set of experiment, is it better to do simulation? Is it better to do an experiment? Pushes that forward, and I don't have to worry about what's the voltage in my electrochemical cell. I don't have to worry necessarily about how to move the X and Y axis. I'm only making suggestions in the hypothesis space of this composition would be interesting for corrosion resistance in this environment. And the rest is hands off for me. I did this about a month ago where we were running a set of experiments at Brookhaven National Lab running X-ray absorption spectroscopy. And I was sitting in my basement writing the code that drove the AI that drove the system. It's real. It's real and it's here. Okay, so let's dive down. My particular material application of interest is in corrosion resistance. I've already discussed the fact that there's a huge financial incentive. I didn't say, but there is a huge split. It's all over through all different types of sectors, DoD, commercial, transport, infrastructure, you name it. There's also a large societal impact. This middle picture is the Bridgeport Speedway Bridge that collapsed while people were leaving the speedway, dumping them out into the highway. This one I think that everyone recognizes as a very recent tragedy. There's a huge social impact to not getting this right. And getting this right means understanding that we have really good thermodynamic models and pretty decent understanding of how corrosion happens, for instance, in single element systems, but that we lack information to be able to make sufficient predictions for more complex systems. And like these Pourbaix diagrams, you can find them for every element. Alloys, they're few and far between. And if you talk to people who do thermodynamic modeling, there's some questions. Okay, so what did we do? We built up an autonomous electrochemical science system, right? The idea was model-driven experiments, and we want to learn about how materials corrode and how things like composition and processing impact their properties and structure. We want to be able to think through the experiment and do it in such a way so that moving forward, we're not just always hill climbing. You'll see a lot of autonomous systems where they're going to the best possible material. That's cool. There's a benefit to that. But we want to also be able to answer more basic scientific questions. So just to show, this is the system that we built. This is an example of looking at a multi-objective optimization, looking at corrosion resistance of nickel-tie aluminum amorphous alloys. The properties of interest are the passivation current, which is the sort of midpoint of this plateau region here, and also the slope. The passivation current tells you how quickly something's corroding. The slope of that plateau gives you some sense of how stable things are. And so inside of this system, we understand that these two properties, corrosion current and slope, go as different. Oh, I got to get rid of the pointer. Apologies. And so what we're able to do is warm start. So this is an example of a machine learning or AI that we're using Gaussian process regression. What that means, right, is that functionally what that means for us is I don't need to start with 100,000 or 100 or 500 or 10 or 20 data points to start my AI rolling. At the beginning of this video, we've taken 3 points and the AI has identified a 4th point to start measuring. And that's all the data that it has. And then it's just trolling through, making predictions with each new measurement, propagating the uncertainty, and then deciding, in this particular case, I believe we were chasing the 95% upper confidence bound for slope, right? So it's just tracking that down, doing a little bit of hill climbing, but at the same time, or no, we're Pareto optimizing. So we're actually looking to find the Pareto optimal combination of these two. Picking the points that make the most sense, and more importantly, leaving most of these points unmeasured because they don't contain, they're not thought to contain by the model, sufficient amount of information to dramatically change predictions. We're only going after the ones that are changing our predictions substantively. And so if you look at the multi-objective optimization, looking for this Pareto optimal front, which basically means that for this particular system, we can't have a perfectly vertical slope and have the minimal corrosion current. And so we have to look for alloys that sort of combine the two. And you can see that within 15 or so points, we've got a pretty good estimate of where that Pareto front is. And from there, you're really just refining it. So you've seen this type of talk before. What's really interesting to us is the extraction out of material science information, right? So one of the things that we sort of focus on is this idea of autonomous phase mapping. And so I mentioned I'm a high throughput experimentalist. If this is one of my 3-inch silicon wafers, each one of these red dots represents a different cut in composition and processing space, so a new sample to be measured. I can take diffraction on each one of these points. That gives me this raw 2D image with some spots indicating that there's some texturing there. We then convert chi theta, integrate through chi to get only theta. We do some data processing and conditioning. And then the idea is that we've taken all of these data, typically on the order of about 500 points per wafer, and we want to generate a phase diagram, a phase map. We want to understand where the phases sit, who are the sufficiently different diffraction patterns inside of this data set. So we often will calculate a similarity metric between them and then use something like hierarchical clustering or spectral clustering to sort of separate these out into individual clusters of unique enough diffraction patterns. Cool. So we make robots with X-ray vision, and I really want to walk you guys through this. So this is an example of a vanadium tantalum oxide binary composition spread. So it means we've got mixtures of vanadium and tantalum in this direction. It undergoes a monoclinic to tetragonal phase transformation with no tantalum at about 65 degrees C. And so we want to be able to map that phase diagram with the minimal number of points. In this instance, we decided we wanted to go with 2 points, right? So you make for free all of the measurements at room temperature. And then you say, okay, we've made this, make a classification using 3 clusters: low temperature, low symmetry, mixed, high temperature, high symmetry phase. And now for the next temperature, with a budget of only 2 points, what measurement do you want to make next? Make that measurement. Hi, y'all. Make the measurement, redo the prediction. This isn't working fantastically. Make the measurement, redo the prediction, What are the next samples you want to measure? The next temperature, and continue. Until eventually you end up with a phase diagram for this particular system, right? And so this is a robot literally mapping out the phase diagram of the native tantalum sample. I don't know why the last measurement in the movie isn't showing. And it's just using the diffraction pattern and the calculation of a similarity metric. And in this case, it's using Gaussian process classifier to generate the classifications and the uncertainties. And so this is cool. But now we get a little bit deeper into the robots doing things, regression task, classification task. But now we start to get to the question of how much do we trust the AI? And I think that a question about how much you trust the AI has to start with the question of how much do you trust the data that you're taking and that others have taken. And so here again, we have this nickel tie aluminum sample. This was done in the 1990s by a group in Japan. They made all of these alloys, measured their diffraction and a couple of other properties, published a paper, and then these gentlemen came after the fact, read their paper, archived only the compositions, and was it amorphous? Was it amorphous plus crystal, or was it crystal? And then later on, we took this data to build models. The problem is when you go back and you think about it, all of this primary data, with the exception of these 4 diffraction patterns, I'm sorry, I dropped the pointer. With the exception of these 4 diffraction patterns, it's gone. I can't, as a scientist interested in amorphous alloys, make a critical evaluation of each one of these points and decide whether or not I believe the attribution of it being a glass or not. More concerning is if I look at these sets of diffraction patterns, despite the fact in the caption they're all said to be amorphous, they don't pass the criteria that I would ordinarily use with my diffraction to identify as something as being amorphous. And so all of that primary data is gone. And the disagreement that we could have had about this isn't captured. It's just in this book, it's a glass and there's nothing you can do about it. So this is problematic for an AI. And this is the why. As scientists, we believe in ground truth. We believe there's causality, right? There's a set of rules that exist that determine the state of matter and its interactions with different external stimuli. We accept that we only have tilde ground truth, right? As scientists, we determine a tilde state using rules for interaction, Bragg's law, idealization of the state of our material, and rules for arrangement. AI doesn't know the difference between tilde ground truth and ground truth. To AI, what you told it, the labels are infallible. That is what that data point is. And they further assume that your data obey all these underlying assumptions that sit beneath it that make their models function. And so if I took a sample like this, there's a ground truth that's unknowable. I approximate it and I say it's a crystalline material based off of this diffraction pattern. But now, because of my bias and the heuristics that I'm using to interpret the data, that diffraction pattern is either a quasi-crystal or just a heavily twinned crystal that needs to be remade, depending upon whether or not you're a 2-time Nobel Prize winner or only a 1-time Nobel Prize winner. This is something that should give us pause, because this means that the predictions we're getting out are just as influenced by our bias in the way that we, first of all, label data, but let's talk about how we acquire data, how we capture the features that we think are important inside of the data. That's all carried along, and the AI is in the end just reproducing what you told it statistically. So to sort of demonstrate this, and we also wanted to get an idea for how do you, in the space where there could be scientific disagreement about labeling of data, how do you use that to quantitatively evaluate the accuracy of machine learning models, we proposed a very simple problem. Here again, this is vanadium niobium oxide. Same thing. There's a phase transformation that happens as a function of temperature from a low temperature, low symmetry phase to a high temperature, high symmetry phase. I believe it's monoclinic to tetragonal. And then you can suppress that transformation by doing ionic substitution. So if you put niobium into the vanadium, you suppress that transformation eventually below room temperature. Issue is when you look at diffraction as a function of temperature for pure vanadium, you get this wonderful bifurcation that indicates to you that you've got a two-phase region, and then eventually, boom, you get a single peak. As a function of composition, that bifurcation never very clearly occurs. And so while it might be relatively easy for pure vanadium to make the labeling of when the transformation has started and when it's completed, I suspected both the humans and the robots would struggle with trying to identify where this transformation started. So what did? We grabbed 5 human high throughput experts, people who've been looking at diffraction data for their entire careers. We grabbed 4 machine learning experts. We gave them the data, said, hey, there's 3 regions, single phase, 2 phase, another single phase. This is the composition region. This is the temperature. These are the samples. Label the data for us. And so this is a comparison of the human and machine labels. The left side, humans only, right side, machines only. We quantify the disagreement by using the Shannon entropy. And so the circles represent the spots where everyone agreed. The bigger circles are where a couple people disagreed. Squares are where more people disagreed. And there is one spot that was a triangle where almost no one agreed. And what we see is that we generally, for the single phase regions, have very large agreement between all of the people who labeled the data set. But that as you hit the boundaries, disagreement suddenly spikes up and doesn't go away until you're sort of firmly into the single phase region after the fact. But that when you sort of average out things using a Gaussian classifier, Gaussian process classifier, you get something that looks reasonable. That looks like a phase diagram that one could expect to see for vanadium, niobium. The machines do less well. The machines do a pretty decent job of identifying the low temperature, low symmetry phase. This boundary actually, to my eyes, doesn't look bad, but then it basically goes off the rails when it comes to identifying where the high temperature, high symmetry phase is. And there's very few ranges where all of the machines agree. That's interesting in of itself, right? But let's talk a little bit about the human labels. And let's talk about this point in particular. This is pure vanadium. It is supposed to, by the literature, have completed the transformation to the high temperature, high symmetry phase by around 65 C. And so this point where there is some disagreement by the literature should be a single phase sample. And we had an expert in vanadium oxide who insisted that this was a single phase sample. And you have to show data with that label as such, because otherwise we're breaking physics. So we have a tension between data as this purely statistical representation of what the actual experiment is telling us and our tilde ground truth. This is a tough nut to crack. And so one of the things that we did was, okay, well, let's assume we have 2 competing models. One model where there's a single phase and one model where there's 2 phases where the low temperature phase is retained. And let's use Bayesian information criteria between these 2 models, and we'll use the Bayesian information criteria one way or the other to demonstrate that, you know, either the 2-phase model or the single-phase model is the superior model. And of course, in this particular instance, according to the Bayesian information criteria, the 2-phase model is superior, but still there's reason to be suspicious. right? We're talking about something that's sitting pretty close to noise. Asymmetry of the peak could be related to the spot size on the sample. The actual measured temperature at the top of the spot might be slightly lower than is being reported by the thermocouple at the sample, at the bottom of the sample. And so there might be good reason to say that this is completely transformed, despite the fact that the statistical model tells us otherwise. And that type of tension wouldn't be captured in a traditional paper where only one person has looked at the data set. And so what we can do now, right, is we can take those information, we can generate our multi-expert labeling, and we can use this to benchmark consensus labels and the associated entropy against different machine learning models. And we learn a lot. Firstly, that as I showed you in the previous image, none of them actually were very good at picking up this high temperature, high symmetry phase. But if you weight the accuracies against the uncertainties of the label, you can see some clear winners, in this case, variational autoencoders for the composition range considered was a winner. But we are also able to identify hidden covariates that strongly influence the relative rankings of the different tools. So one hidden covariate is the number of clusters you allow in your unsupervised technique. Another is how far out in composition you go. So, this is an example for one particular model where if I stop here and I don't consider anything to the right of 20 atomic percent niobia, that's actually the best model. But as I allow more data, that model gets progressively worse. And so these are the types of things that we have to be thinking about as we're generating and extracting data from the literature and testing our models, that if these aren't captured, whatever the prediction from your model is, if it's good, you're happy, you're good to go, let's do it. But it might not be a representation of the actual physical state of your material so much as a representation of your own biased interpretation of the physical state of the material. Okay, so I got a couple of minutes left. I want to talk about incorporating AI into physical models, and I'm just going to use a toy example. I'll skip the actual data because it's interesting. There's this traditional, again, tension between the use of AI, which is infinitely flexible but extrapolates poorly, and physical models, which are able to extrapolate very nicely under their ranges of applicability, but are inflexible. And so if we consider a data set, choose your favorite, this is grain size strengthening in metals. You can look at a couple of data points, take them, and say as the grain size gets smaller, it looks like this Y variable gets larger within error. And you can fit a Gaussian process to it, right? You can fit your favorite AI model to it, and it'll interpolate very nicely with uncertainty bounds. And then depending on how well your uncertainty is quantified or calibrated, as you push off, the model will tell you it's getting worse and worse, and that's life. Conversely, you can fit your favorite physical model, Hall patch, right? The same model, get as good a fit within those set of data, and then maybe get a little bit of physical insight. But there's an opportunity, right? I can take more data. And when I take more data, I see that my AI model was not only wrong, but was very overconfident about how well it was doing. But that's fine, right? We understand that there is the possibility, even inside of this data set, that I might hit a new mechanism. I might hit a new physical mechanism that's going to break my physical model, right? When the grain size gets too small, Hall patch breaks down because you no longer can speak of dislocation sliding quite the same way. And now my AI model looks like the stronger model. So here's the idea. You can treat your physical model in a Bayesian way. You can treat each one of these variables, these fitting parameters, as a GP, right? And so these can actually be predicted using Bayesian inference. And you can actually, from that data set, get out a prediction of what each of these parameters are with an uncertainty associated with them. But then you can also build in a sort of slush factor, another GP that maybe doesn't have this, or maybe it has composition or temperature inside of it, that when this model turns bad, that model turns on. And so a good example, this is an example of using it, for instance, in corrosion resistance, where we understand that there is a Hall-Petch relationship between data, between the grain size and the corrosion, but that there is an unquantifiable, there's a rule that we don't know the mathematical form for that determines how composition is going to impact the corrosion rate. And now you've got a scientifically informed model that when this term dominates, you can use, and you can use it to pull out your Hall-Petch relationship, for instance. But when composition now becomes a larger role, you have this sort of slush factor inside of your model. Okay, I'm just about out of time. And throughout the talk, I've been laying breadcrumbs, and I really want to nail them home now and sort of bring home the main point about how robots are going to teach us to trust AI. The first and most important is that the data are born digital and structured. You get the data and the metadata for free because it's all being pushed forward using your AI. That soup to nuts provenance and label analysis can be done afterward by individual or multiple users and can be fed back into the AI to give new calibrated uncertainties. You have a homogeneous data source. You're no longer building data sets from 100 different papers from 20 different groups and maybe 150 different graduate students spread across the world. So you don't have this lab to lab or person to person variation that one oftentimes expects in the technical literature. Those are eliminated. It lowers the reluctance barrier because it becomes a substrate for scientists to rationally interact with. They can test their models, they can validate or they can invalidate them, and they can refine them as they're going along as new observations come that push against their sort of set biases. It's a method of educating us about the strengths and weaknesses and the follies of the existing AI models. And because we don't have the same reluctance to do out-of-the-box experiments because they're easier and less time-consuming, they encourage us to rethink our assumptions about what are the driving forces for things like material stability and properties. They allow us to look at experiments and say, hey, look, the AI is predicting this experiment will have this outcome. My physical intuition tells me the exact opposite. And maybe I've got a third model that says Sunday. That's a really interesting experiment. Maybe I should do that rather than just trust my gut. All right. With that, I'm at 50 minutes. I think that's just about ideal. I conclude my talk, and I really welcome your questions. Thank you all for your attention.
Thank you very much, Jason. That was great. The floor is open to questions. If someone has a question, you can feel free to raise your hand in the reactions portion of your tools, and we can unmute you and allow you to ask the question. You can also, I think that Sam has allowed everyone to unmute themselves. So we'll start with Cheyenne. Feel free to unmute yourself and ask the question.
Hello, thanks for the very interesting talk. Thank you so much. Actually, I have some questions regarding the AI backend that you have used. I know that somewhere you mentioned we've used the variational autoencoders, but somewhere else in the talk, you've been mentioning bonusing on the correct predictions. So I was confusing the method that you have used for doing this extrapolation. Are they deep learning only, which defines them to be variational autoencoder, as you mentioned, or you had sometimes you've been using reinforcement learning and other techniques at the same time? I really appreciate to ask this question. Plus, I had another question regarding the collaborations, because I think material scientists at different areas right now are working on AI and other topics like that, but they work in their own bubble. There is no way for them to connect with each other, use their understanding of AI and how they have used AI together to kind of make application of AI in this field faster. How do you actually address that? How we can actually make more people collaborate with each other in the field of materials and AI? Thank you so much.
Okay, that's a fantastic question. And I would like to point to the sort of beginning of my talk. I tend to think of the sort of machine learning techniques we're using as tools, and we will often use them in stacks. So I don't, so good example. This is using spectral clustering to identify for each one of the diffraction patterns that's been taken, how distinct are they? They are using actually a distance metric. If I'm not mistaken, it's using the cosine distance between each of the diffraction patterns, which we then feed into spectral clustering. Spectral clustering gives you, for that composition and temperature, a label for each diffraction pattern that you've acquired. And so what we use afterwards is we train a Gaussian process classifier on the data set that we've taken. And that's actually what makes the predictions for the other classifications for data points that haven't been performed. In the case of the metallic glass work and the thermoelectric work as well, which I talked a little bit about, random forest is our primary sort of go-to. Random forest is just brutal. It's just so good. It's just so good. It's an explainable model. There's all sorts of issues that people don't quite understand when it comes to training their model, but it's brutal. I was talking about XAS. In the XAS example, I was actually taking the raw spectra, projecting them into latent variable space using principal components analysis, using those principal components to train a Gaussian mixture model to cluster them, and then again using a Gaussian process classifier to project from that training set into all prediction space.
Interesting. So you've been, I'm sorry. So you've been using dimensionality reductions for kind of classifying your space. Really nice.
Often is the case. In other examples where I'm just working with colleagues that are doing simpler data, additive manufacturing like processing and composition and structure, we sometimes use random forest, sometimes a decision tree or decision table is sufficient to be able to make accurate predictions. You use the tool that works. And sometimes you gotta stack them.
Wonderful. Have you been thinking about using deep learning? Because with knowing some data from experiments and simulating some others, I've been working with deep learning for signal processing and signal prediction, and they also are really powerful in their response.
It's a great question. To this moment, I haven't been using them just because I like to think about it this way. I want the simplest possible model. If at all possible, I want to use a decision tree or linear regression like Lasso, where I drop out features and I just get the slope that makes the most sense, right? Because I want something interpretable. I want something I can look at the model and understand why it made the prediction. Sometimes we have to step up to a more complex model. We have to jump up to random forest because the data are too rich. There's too many different things going on. In which case now we're in the world of explainable model, where I've got to use something like feature importance to be able to understand why the model made the decisions it did. That's a model sitting on top of a model. But yes, I can think of a couple of projects we're thinking about starting where we're not going to have that luxury, at least to start with. And we're going to have to start considering things like neural networks. And we'll see where that takes us.
Thank you so much. Thanks for the answers and discussion. It was really nice.
Thank you for the question.
Okay.
Over.
I think there's a question from, is it Jan Pols? You can feel free to unmute.
Yeah, thank you, Jason. And I have a question to your experimental data, basically. So your data is basically lots of points, but how reliable is your characterization technique? So how sure are you that it's 0.01% of niobium? And especially, would it not change by, sorry, the sound in my head, I can't hear anything.
Can I try to rephrase the question?
Yeah, sorry, I can't hear anything.
Sure. I'm sorry, did you say you can't hear me?
I'm sorry, there's some background noise at the moment.
Uh-oh.
Okay. I don't know quite where that's coming from. So you basically have two types of uncertainties, right? You have an uncertainty in this particular instance, like consider this diffraction pattern. You have an uncertainty in your feature, right? What is your niobium concentration? What is your temperature? In principle, you can bring those along. In this particular instance, we didn't quantify that uncertainty and propagate it. That would be interesting, and we should in the future. And then you have your measurement error, right? So what's the signal to noise? How confident are you in your attribution of monoclinic versus tetragonal at a particular temperature or multi-phase? And how do SNR sort of, how to say this, convolute or work together to obscure your ability to make an accurate representation? We're actually looking specifically at that in the context of diffraction right now, and I hope to have that paper out by the end of this year. What you can, the sort of short answer to it is you can only provide a statistical representation and say, we can say with this amount of confidence that it is a single phase high entropy alloy with no evidence of intermetallic ordering, so long as grain size for this or new strain inside of it is above or below a certain threshold.
Okay, thanks. It was kind of a different question because I wrote a paper about this, that the data of the, for example, the Pearson crystallographic data set has quite a large error. And this error, for example, silicon dioxide is reported in 54 different crystallographic space groups. So you don't know which one is right, which one is wrong. So you have to choose one of them or two of them. But this data makes kind of confuse your AI because he doesn't know which is right, which is wrong. So you have to basically decide for him which one you would choose. And I don't understand how you did.
Yeah, I mean, there are different ways of approaching that, right? Particularly for, in the case where there's a bunch of different structures, generally you have options, right? Option number one is if you want to stick with compositional features, right? You want to just describe your material as a composition, then you sort of have to make a decision about how far above the convex hull you're willing to accept a structure as being stable. And then you have the option of training a variety of sort of sequential models where you pull one structure in, push one structure out, and sort of generating a statistical prediction of what are the possible structures for a new material. The other opportunity, Kamal Chowdhury at NIST does this. I think it's brilliant. he doesn't just describe materials as compositions, but he also describes them in terms of their structure and their ordering. And so his feature set, maybe a bit larger than I would like, normally speaking, but basically incorporates the radial distribution function for the different elements. And so from that, you've got a method of discriminating between the different types of silicon dioxide that are present in something like the materials project data set, and then train models from there. And then you sort of, again, have the same problem of how far above the convex hull am I willing to accept something as being metastable but synthesizable. But that's sort of its own really interesting problem. I hope that helps.
Yeah, thank you. That was actually a topic of my paper. We can look into it. And
Okay. Thanks very much. Thank you for all the questions. And Jason, thank you very much for the great seminar. On behalf of everyone in the audience and the BIMR, I'd like to really thank you for taking the time to give this seminar. Those that are on the call, I'll also make this seminar available on our new YouTube channel on the BIMR, and I'll have links to that posted. Okay, with that, thank you one more time, and thanks everyone for joining in to this seminar. Have a great weekend, and we'll stop there.
All right, thank you all again for your attention. Thank you, Hatem.
Yeah.
Take care, y'all.